Next speaker is Kevin Boyack from SciTech Strategies. I had his bio up here. He's been at SciTech since about 2007. Before that, he was at Sandia Labs, and interesting in the notes, he was one of the things he worked on was socioeconomic war games. So I'm not sure if I would have invited him here to speak if I knew that, but he's going to talk about the map of science and what's the last part of that? The analytics of publishing.
So I'd like to thank Dave for inviting me here to speak. It's interesting coming to speak to an audience that you know only a little bit about, because you're never sure whether you're going to hit the target or not. So you can tell me after the talk whether I hit the target. Just to segue a little bit from the previous talk, you know, I too am a baseball fan, not nearly to the degree I think that Dave is, but and played a little bit of high school ball. And so my one claim to fame when it comes to baseball is that I went to Poway High School in San Diego, and Billy Beane, who is the general manager of the Oakland Athletics, and who was one of the main figures in Moneyball. And in any case, he went to the neighboring high school, our rival high school, and I happened to face him once, and he hit me. So I got hit by a pitch by Billy Beane and promptly got stranded on first base. So, and of course he went on to have a great baseball career, and I'm here giving a talk on visualization. So, okay, so we're going to talk a little bit about the mapping of science. Okay, I think I figured out the buttons here. So why am I here? Why would Dave have invited me? Well, it's going to be a different talk than what you heard, and by the way, kind of a hard act to follow because you tell great stories. But I'm here to answer three questions. The first is, what is a science map? Second would be, how do you make one? And the third is, once you do all of that, what can you do with it? And I'm going to spend only just a little bit of time on the first two questions. Most of the talk will be looking at some examples on how to answer the last of those questions, the actual analytics involved in looking at a map of science. So what is a science map? Well, if you think of a regular map or of a geographic map, and I'll put up a picture of one here, a map is a visual representation of some sort of information space. So this map that you see here is something that's obvious to all of us. It's a map of the United States. We've got borders indicating the states. And this map is a template. I'm going to call that a template for other information. And in this case, the colors show annual precipitation in various parts of the country. So you've got a map. It's something that we've come to understand from its shape, from the borders and lines on it, and then you overlay other information on it. Well, a science map follows the same kind of underpinning. So you create a space that you can learn, and then you can use that as a space on which to organize or display other information. And what the map does is it shows pieces of things and those relationships between the pieces. And as I mentioned, it gives you a chance to organize other information with respect to that. So I thought I'd also put up one other United States map. This one, you recognize that. This is the map of baseball fandom from the New York Times. So again, we have the United States here, and the colors show the dominant fan bases of different teams and where they are. And so if you go to the New York Times website, you can look at this and you can drill in, and county by county you can see the distributions of the fan bases for different teams. And as you can imagine, they're very geographically centered around the team that's located in a particular area, with the exceptions of the Yankees and the Red Sox, which have fan bases across the entire country. Okay, so let's jump from that to a science map. This is the picture of a science map. It's totally Greek to most of you, I'm sure. But let me give you a little bit of a flavor of what we've got here. This particular picture represents 43 million documents. Okay, so talking about large data, we've got some large data here. And we've clustered the documents, and each cluster is represented by a dot. And in this case, we've colored them. And so the math and physics dominated clusters are in purple, computer sciences are in pink, engineering's in light blue, chemistry's in dark blue. All of the medical areas are down at the bottom, and they're different shades of red. The darker the red, the more likely it'll kill you. The lighter the red, the more likely it's something you can deal with. And then that kind of light orange in the middle are the social sciences. Green is biology. So we've picked colors that kind of represent what we might naturally associate with different fields of science. You know, the reds represent blood, the greens represent trees, the browns represent soil, purple being physics and math or the royal sciences and so on. So once you get a feel for this map, then you can use it as a template on which to show other information. Okay, so that's what a science map is. How do you make one? Well, the first thing you do is you select a data source and the objects that you want to have as the pieces of your map. So, for instance, papers or patents or grants or other types of things. It could be authors, it could be words. And then you calculate the similarity between pairs of objects, variety of methods for doing that, and then you create the visual map of those objects based on the similarities. There's a lot of math and a lot of database work behind that. But let me give you a simple example of how this might be done. So in this case, what I've done is I'm from a small company. There are 3 of us who are principals in this company. And over the years, we've published some papers. So between the 3 of us, these are the papers that we've published in the last 15 years. And I've just stuck them in a circle because at this point, you don't know what the relationships between those are. But I've taken this set of about 40 papers. Each one of them is colored by the principal author, and the size of that dot represents how many times they've been cited. So you can see the one up at the top, the red one is the most highly cited of these papers, and so on. So we select the data. Well, the next thing we're going to do is calculate the similarity between these pairs of papers. Now you can see that some of them are, and this is represented by the width of the line, some of them are very similar to each other. Others, there's no lines between at all because there's no similarity between them. But we take this whole group of similarities and say, okay, let's organize this in a way that visually makes sense, and you end up with something like this. So now what we see is that whole mess of stuff actually fits into 2 very nicely distinct groups. Okay? The one on the left has to do with mapping science. The one on the right has to do with the context of the text involved with citations. Okay, so they are related topics, but they are distinct from each other. So this is the process that one might use to develop a science map. Now, of course, it can be done with different data sets, different scales. This is only 40 papers, and the picture I showed you previously had 43 million documents in it. So there's a lot of variation in the ways that these can be done. Well, once you have a science map, what can you do with it? What are the analytics that are possible? And this is just going to give you a sampling of the types of things that people can do. So, as I mentioned, creating a science map, you're creating a visual depiction of the topic space associated with scientific inquiry. And I really enjoyed your comment about science being about questions. That's something that we would agree with. And furthermore, the thing that we find as we analyze publication data is that we think that most of the time the question isn't answered. And I'm sure a lot of scientists would take issue with that. I think that most times what they're doing is reframing the question. They haven't really answered the question. They've just gone and said, well, no, it's not really this. Let me move over here and reframe this question and look at it a different way. That's the majority of, in my opinion, of what's happening in science, and these maps and the publication streams reflect that. Okay, so that's kind of an aside, but these maps give us an opportunity to look at those types of things. So in terms of, from a publication standpoint, from a publisher standpoint, what types of questions might one answer with a science map? Well, the first thing to do is to look at the overall structure. What does the science look like? And what kinds of hypotheses could we generate from that structure? Portfolios. Where is my stuff? Where are my journals within this space? What does influence look like in a map of science? Okay, we hear about impact factor, we hear about H indices and all of these things. What does influence look like in a map? What are the trends and dynamics? What's emerging? What's ready to die? What should have died but hasn't died yet? There's plenty of that. We can visualize views and downloads. I'm not going to go into that because I don't have those data. Maps can be a basis for metrics. Okay, that's something that I think is going to be more important in the future. And I think I'll probably delete this thing about reviewer recommendation because a lot of people do that, and we've each got a little thing in front of us at our tables about a very nice recommendation system. So what I have is conceptually we can do that, but it's not our forte. Now, I should put one quick disclaimer, and that is from a publisher standpoint, there's all these questions that you guys have that relate to your financials and relate to who do we target in terms of subscriptions. We don't answer that with publication data. So this is more the conceptual side of the topic space that's covered in publications. Okay, so a mini agenda for the rest of the talk, talking about the analysis portion. I'm going to talk about this notion of content versus context. Go briefly again over some sample questions, show you our maps, and then go through some sample analyses. So this notion of content and context is something that we feel is really important, and part of that is because most of the people who create maps of science, they generate maps which I would call content maps or local maps. So they'll take their little chunk of data. The map that I showed you where it was my 40 publications, or the 40 publications from our team, that is a local map. That is a content-based map. That doesn't place that information within the context of broader science and what's going on. So if you're doing a content-based map, all you have to look at is your own stuff, your own data. But if you want to place that within the context of what's going on in the world, then it requires more data than just the data that you have. Perhaps the baseball analogy would be, you can look at what's going on for one team, but if you want to understand the context of what's happening in baseball as a whole, you need all of the years and all of the teams. A content-based map is very focused, and it can give you answers to focused questions. The context-based map is very broad. The content-based map is very computationally tractable, fairly easy to do, something that most people can do on their own with software that's available, freely downloaded. But if you want to really see the competitive context, you need the broader map. So an example of a particular question and how it might be answered from a content perspective versus a context perspective. Let's say you have a particular portfolio of journals, and you want to know what the emerging trends are associated with those journals. Now, I'm going to, for purposes of this argument, assume that for this set of journals, you've got some sort of a taxonomy or indexing system that pulls the keywords out, and so you've got that listing for each one of the articles in those journals. Well, on the content-based approach, then all you have to do is count those keywords, those taxonomy terms up, and look for the ones that are new and that are growing very quickly. Those are the emerging topics within your portfolio of journals. Okay, that's a simple exercise, something that can be done just with your own data. What that doesn't tell you, though, is whether the thing that's emerging in your portfolio of journals is emerging overall. It's something that might have been quite common in the entire world of science before that, and it's something that just recently got picked up in your portfolio of journals. So to do the broader contextual analysis, one needs a much larger data set. For instance, all of the Web of Science, or all of Scopus, or all of PubMed. And then you do the exact same process. Count up all of the keywords and see what the emerging trends are, and then go back and find where your data are within that, because then you can compare the trends within your data to the trends overall. So that's an example of content and context. So back to questions. And this mirrors pretty much what I had on the previous slide, so I'll just go through this very quickly. The first one is structure related. What does the topic space look like? what things are related to each other, what are the trends, what's emerging and declining. From a portfolio perspective, what topic areas are core to a particular portfolio, which ones are peripheral, where are things thick and thin and dense and not dense. Are the let's say you've got several different journals. Are those journals really different from each other in what they're covering from an overall science perspective? Does a particular publication, a particular journal, influence a broader topic space, or is its influence very stovepiped within just the set of topics that it covers? What are potential expansion points? If you've got a taxonomy, you might want to evaluate the taxonomy. Where are the terms very well posed, and where they might need to be split up or defined in a different way? And then I'll go to the bottom one. What role do books play? Because I know we're talking a lot about journal publications, perhaps conference publications, but books are something that are very much a part of your world, but have not traditionally been part of the databases that, for instance, I look at. Okay, so a little bit about our maps. We tend to make very large maps, and when I say map, here what we do is, as I showed in the previous slide, we generate a classification system, so to speak, by doing clustering. And so we'll take, in this case, 43 million documents from Scopus, and we'll cluster that, and it turned out in this particular map there's about 150,000 separate clusters. And each one of those contains a history. So we know which documents are in that cluster, and we can see what has happened over time in that very tightly focused topic area. One thing that I think is really interesting, and this is fairly new in our world of mapping science, and that is that we included the non-indexed, the non-source materials in this map. So Scopus and the Web of Science, they index a set of journals and conference proceedings. And those are the primary source materials. But since they are citation databases, they contain the references to other things in those reference lists, things that are not necessarily indexed in the database. And so if we include those things in the map, we have a much broader context that we can look at. And that includes things like books. It could include New York Times articles and various other things. Okay, so now we'll get to the pictures. And I'll go through on the left. You'll see there are a variety of types of analyses that I'm going to show you. One point that I'll make a couple of times, but I'm going to make it before I even get into this, is that these are the pictures. This is the last 2% of the effort. Okay, there's all of the work that goes in advance to create the map and to have all the data fielded in various ways in the database. And so we know everything that's in each cluster. It's all based on mathematical analysis. The pictures are just a way to represent that mathematical analysis. And so for more details, we simply go back to the tables from which the pictures were generated. Okay, so first thing I wanted to do is, and I'm going to pick on Dave here. He hasn't seen this example before, but we're going to do a portfolio comparison here. And so I took 6 or 7 journals from the American Chemical Society, and we're going to show where the papers in that journal are located on the map. Okay, so this is JACS. This is the Journal of the American Chemical Society, and you can see that it covers, the blue dots are all chemistry-related areas. The pink ones down at the bottom are more medical. But JACS covers chemistry very broadly, which is what you would expect from the broad headline journal for chemistry. Now let's look at, for instance, the Journal of Physical Chemistry B. It's a different profile, but there is some overlap with JACS. So let me go back and forth between these two. You can see that there's far less down in the medical areas, and there's a portion that overlaps with JACS there. Let me move to the next one. This is now inorganic chemistry. This one is very different from the Physical Chemistry Journal. So I'll toggle back and forth. You would expect it to be, because they've got very different names. They're from discipline-sized areas of chemistry. So just from a visual perspective, we can say that JPhysChem B and inorganic chemistry are quite different. So now let's move to Journal of Organic Chemistry. Once again, it's a different profile. And from this, I can actually say, well, organic chemistry is pretty much those dots that are big in blue here, whereas inorganic chemistry are pretty much those dots over there that are blue. So I can visually compare these journals. Let's go to analytical chemistry. Once again, a different profile from organic and inorganic chemistry. Journal of Medicinal Chemistry. Now this is really interesting. Very little in the blue area. There's a lot down in the red areas and in the yellow areas. So most of the medicinal chemistry papers are actually commingled with papers in medicine rather than papers in chemistry. And finally, let's look at the Journal of Agriculture and Food Chemistry. Again, a very, very different profile. You can see most of that is down in an area which would be food chemistry, food sciences, with some biology-related papers as well. So this is a visual picture of how one might do a portfolio comparison analysis among a set of journals. Okay, so let's look at the idea of influence from a visual standpoint. And I'll pick one of these journals that we just showed, Inorganic Chemistry. And this is the profile of the papers that are published in that journal over the past 5 years. So influence might be shown by showing the positions of the papers that cite these papers. So let me go to that slide. Did you notice a difference as I toggle back and forth? There's very little difference at all. Okay? There's one spot, you can see there's one dot kind of at the upper right of that band of dark blue, and let me circle that. That was the one node that grew significantly when we changed from the paper profile to the impact profile. And so that, to me, would be a candidate for inorganic chemistry to say, our papers there are of much higher impact than our portfolio would suggest on the whole. So maybe we want to increase our position in that set of topics because our papers are obviously of much higher than average impact in that area. Those are the dominant topics associated with that chunk right there. So that's the type of analysis that can be done regarding impact with a broad database and with mapping techniques. Okay, what about trends? We went through and using this map and some other things, we identified there's 150,000 separate clusters here. And what we did is we used some metrics to pick out the 25 in 2010 that seemed the most emergent to us, based on their publication profiles and citation profiles. And so those 25, I got ahead of myself. So let me set that aside and just go through trends. This is going to show the publication trend over time for one journal. And this, I've cherry-picked this journal because it's the one that has grown the most over the past 5 years. And so the trends show up very well. But as most of you know, PLOS One is now the single largest journal in the world in terms of publications per year. But back in 2006, it was really small. And you can see that the papers were pretty much in medicine and in biology. And in 2007, not only did those areas grow, but a lot of other adjacent areas started receiving publications. And then in 2008, it grew again, both in terms of numbers in particular areas and in its topic spread. And the same thing in 2009. This just continues to grow, as you can see here. And you can see areas that are focused and more. There's more going on there than in other areas for PLOS One. There's some neurosciences in that band of yellows. But the other thing you can see here is that even though it's a multidisciplinary journal, there's very little in that journal from the physical sciences. There's almost nothing in the top half of the map as compared to what's in the bottom half of the map. Okay, let me get back to the emerging topics. As I mentioned a minute ago, we picked the 25 most emergent topics in 2010, and this is where they are located on the map. Okay, so to give you an idea of what some of those are, we have high temperature superconductivity, which of course, you know, superconductivity has gone through several phases, but when they find a new material that they previously didn't think was going to be superconducting, and then they find out that it is, then research takes off in that area once again. So high temperature superconductivity took off in fact, 2008 and stayed huge over the next several years. We've got several topics related to graphene, several related to cognitive radio. We've got 64-slice tomography and flu pandemic related research down at the bottom. And 25 is not a magic number. We could have taken the top 50 or top 100. The fact is, though, that we can rank topic spaces based on the characteristics of the clusters and find which things are popping, are hot at a particular point in time. Okay. And this work was just recently published in the journal Research Policy. If we want to look at the actual cluster histories and how the clusters relate to each other, we can generate plots kind of like this. I'm not going to go into detail on this, other than to say that this shows that graphene was known for a lot of years, but it wasn't until 2005 when it became a really hot topic because somebody figured out how to separate it and actually make it useful. And of course, that generated a Nobel Prize several years later. Okay, what about taxonomies? I know that lots of publishers have taxonomies, sets of controlled vocabularies that are used to tag their papers and that they keep track of things that way. And so we did a project where we looked, in fact, at the PLOS taxonomy. And it's interesting how we tried several things to actually map their taxonomy. We tried some things where we just took those terms in their taxonomy, tried to relate them to each other, and come up with a separate map of the taxonomy space. And those efforts all met with varying levels of success. What we ended up finally doing is triangulating the position of each one of their taxonomy terms onto our map using all of Scopus's data. And so you can see the distribution of the taxonomy terms. Now, if you want to look specifically at the terms in their biology section, you can see that most of them clump together in a biology-related part of the map. But you've got some terms up at the top of the map that are up in computer science and engineering. You might wonder, what are those doing up there? So let's take a look at a few of those. You can see that some of these terms, like circuit models, that has a very specific meaning in biology, but it has a very different meaning in electrical engineering. Now, PLOS is very much a biology journal, and so they weren't worried about the different meanings that are potentially associated with this, but it served notice that maybe in the future they might want to change the rule base a little bit to allow them to have a tighter focus on that term in the biology space. Okay. So I'll go ahead and skip the recommender thing and just mention, and this is a slightly different picture than the one I showed earlier because it's a different map. But this is our non-source map. It includes those 22 million non-source items. And what's interesting about this one, and the picture's not going to show up because it's underneath, but we could show you where all of the New York Times articles that are cited are on that map. And they turn out to be, unsurprisingly, mostly in the social sciences and humanities. Very few, relatively speaking, New York Times articles are cited from the hard sciences or from medicine. It's mostly in the social sciences. But what about books? Well, this is where books are in this map. There's not an area of science that doesn't have foundation in books. Now, you can see from the sizes of the different dots that they're much more prevalent in the social sciences. But also there's a lot in computer science. There's a surprising amount up in the geosciences. There's a lot in engineering, far less in chemistry and in physics. But the thing that was fascinating to me about this is that books are underpinning almost all of this, well, all of the sciences to some degree. And we now have the ability to show that, show where these books are positioned and how they are influencing the trajectories of science. So, once again, all of the visualizations are based on tabular data from a database. So, although the pictures show you kind of what's going on, the numbers are far more meaningful. Okay, how might one get started on this? If you want to try it yourself using your own data, the thing to do is search for Indiana University Sci2. The The first hit will be their website. You can download this software. It's got all kinds of, it's got very good documentation, lots of different algorithms in it, and it can be used to generate maps of your own data. It's a very good tool. If you want a much broader and contextual analysis, you need to talk to somebody like us if you don't want to spend a year trying to figure out what's going on. And that's us. And well, I'll quit with this. You can read this. But science mapping is a lot of fun, and I think it has a lot of value in terms of publication analytics. So thank you very much.